So I hope that the little discussion, clarification I added on Slack this morning makes the discussion we had, the argument, the subject I discussed in the last 15 minutes of the lecture of yesterday less confused. Let me continue along that line, and also with some examples in a moment. Examples are essential to understand the issue. Okay, so what I want to discuss is how to make all this reasoning of yesterday into something more concrete in our way of evaluating theories. Okay, so and here I am going to present in a slightly different way than it was originally presented, but the NDS is exactly the same. The naturalness criterion of Toft. Okay, it's a criterion. Okay, you should take it for what it is. It's a criterion. We may discuss that, whether you want to take it or not, but let's press on. Okay, so the question that Toft was asking is, under what condition is a quantum field theory, or the parameters of a quantum field theory, natural? Okay, as I insist, it shouldn't be natural necessarily, but under what condition, with the definition we gave of naturalness, under what condition is a QFT natural? Now, we should understand this in the following way, because we should always think, and of course this was not emphasized in 1979, although it was clear to everybody, but it was less emphasized, that when we think of quantum field theory, we always think of an effective field theory, okay? And so therefore we have the usual cartoon, okay? There is some, you see my pointer?
Yeah, we can see it.
Okay, there is some more fundamental description described by parameters GA. Again, they can be an infinite set, but this more fundamental description itself, at least in the cases we have been seeing so far, is an effective description that breaks down at even higher scales. But by the time you go down from the higher scale to this lower scale lambda, now the scale lambda is the infrared scale of some UV physics. And for us, doing experiment below here, it's our UV scale. At the scale lambda, the number of parameters that really matter will not be infinite. Okay, of course, it will depend on the precision of what you can measure, but okay, these GA are formally an infinite set of parameters, but in practice, they are a finite set. As you have seen yesterday in QCD, there is the QCD scale, the mass of the quarks, and alpha electromagnetic, okay, at the truly important level. Then you can refine it, and in the usual way. In fact, the scale lambda itself that describes the change of regime between the UV and the IR, you can view it as part of these parameters, okay, like in the case of QCD. Okay, now, and so writing the effective theory, it just amounts to computing observables in a two-step procedure. We first integrate out degrees of freedom, short distance degrees of freedom, and we derive an effective Lagrangian in terms of the long distance degrees of freedom. And then we use these effective Lagrangian to compute observables. Of course, we could have done it in one shot. The observables would have been function of these more fundamental parameters. However, let's assume that when we do effective theory, what we have done, we have integrated out this UV physics, which we may not know. Okay, in general, we don't know what it is. In the case of QCD, we knew it. In fact, we know it now, but we didn't know it 60 years ago. Okay, or in fact, yeah, around 50 years ago, we didn't know. And but it's always imagined there is some more fundamental physics, we integrate it out. And the effective parameters, the parameters of the effective Lagrangian will be functions, will be depending on fundamental parameters of our theory in this way. And this relation, like all relations in physics, will be covariant. With respect to the symmetries. The symmetries, all the symmetries we can think of, symmetries under which the parameters themselves transform, okay? Okay. Which is to say that this expression here respects the selection rules. Again, we are doing quantum mechanics. So in quantum mechanics, every quantity is affected, every quantity is determined by some amplitude, okay? At the end of the day, you talk about the mass is the 2-point amplitude, okay? Controls the propagator. The coupling is the 2-to-2 scattering amplitude. They're all amplitudes. And in quantum mechanics, these amplitudes are computed by integrating our functional integral, in other words, by summing over configurations. And that's the essence of quantum mechanics. You're forced to sum over all configurations. In other words, quantum mechanics takes into account all that can happen, okay? It probes all configurations. So all contributions that respect the selection rules will appear, okay? So this coupling will be, normally, they are like a sum over all possible contributions, which can, very roughly, they are like the sum over the possible amplitude that contribute. And you already seen it. Again, what we have seen for the pion mass is of this type. There are two contributions to the pi zero, pi plus mass difference. One is coming from diagrams with the photon. The other is coming from effects that we cannot even write fully in the Feynman diagrams because QCD is strongly coupled at the scale where this happens, but are related to the quark masses. Okay? So in a sense, in that case, we have two broad amplitudes that contribute. But in general, we will have many more and at higher order. So, I mean, every parameter can contribute at higher and higher order. Like in the case of the pion mass, we computed the leading order in the electromagnetic coupling, but there are contributions at higher orders. So all that can happen happens. This is, if you want, is the rule in quantum mechanics. This is in the sense, this is Gell-Mann's totalitarian principles. All that is possible in quantum mechanics is compulsory. Okay. Okay, and now for the dependence of this GI, for the final result of this GI, we can apply the notion of naturalness. If among all these contributions, if the selection rules are not enough to account for the quantitative value of GI, it means that, in other words, that there are some accidents or cancellation, we say the situation is unnatural. It doesn't mean that this is impossible, just call it unnatural. And the natural situation, which is the one that is undoubtedly more usual, is that no such thing happens, and then the size of this object is of each coupling is accounted reasonably well by the selection rules. In other words, if there is a leading contribution, there will be just one. There will not be another one comparable that cancels the result. Although that, again, it's perfectly possible. Okay, so now, said this way, it seems like that in order to discuss naturalness, we need to know the UV theory, but actually we don't, okay? And we don't for the following reason. You can imagine to write, imagine you take one certain coupling of the effective theory, okay? Or some combination of couplings. You should view, again, this coupling as an object or part of a multiplet that transforms under some symmetry. In other words, this coupling, you can always view them as fields, if you want. We call them spurions that transform under symmetry. We have seen that already in all the examples we have done. Okay, we have done it for the quark masses. We've done it for the charge operators in the pion mass. We have done it for the length of a pendulum and the strength of gravity in the case of the pendulum. So you can imagine, okay, writing expressions of this type involving only the low energy couplings you can say that here GI different than GI1. In other words, in principle, you can often write, you can basically always write expressions that where one of the low energy coupling, where, in other words, where you can use n-1, let's say that you have n couplings in low energy theory, you can use n-1 of them to write an expression that transforms under all the symmetry like the nth expression. In other words, yeah, you write an expression like this, okay? Let me say it this way, perhaps I should say it better, okay? Yeah, you can write, well, I should not say this, you can write, let me use the symbol here. This means, this square here means transforms in the same way, okay? It has the same quantum numbers, doesn't mean that it's equal. I just say that you can use your part of your low energy couplings to form an expression that transforms precisely like another coupling. I should add that in this reasoning, you are allowed to use also the cutoff as an assumption, because this is a scale and this will enter matching just dimensions, okay? And again, we have seen this happening for the pi of mass. Of course, this fundamental scale here, the UV scale, is embedded in the higher dimension operator that you have in your effective theory. In particular, if you look at the derivative expansion, when you compute something, you look at terms with more derivatives, the parameter that controls this expansion is precisely the cutoff. So you can deduce, ideally, if you have enough power of measurement, what this cutoff is. So you can consider it as part of the parameter. Otherwise, you just assume it. You just let's assume that if I measure this, it would have this order of magnitude. Now, then it's very simple. Now, this GI here, okay, this GI here, in reality, are functions, okay, of the capital A, or the fundamental couplings. I don't know, maybe I'm doing something truly so formal for such a stupid thing as natural, but let's do it. But be patient, okay? And maybe I'm making a fool of myself, but let me just, now you see, what is this? This is an expression where, which is made purely, it's just a function of the UV couplings. And this is an expression that satisfies all selection rules. It has exactly the quantum numbers of this one. Okay, so this is an expression that can appear in the fundamental relation for GI1. Okay, this term here, we have concocted a certain expression, which in the fundamental theory is written in terms of fundamental couplings. But we can also write it in terms of the effective couplings. The crucial thing is that this guy here is something that can appear in the expression, is one of the amplitude that can appear. Okay, so we can certainly estimate with this trick some of the contributions. And then if the value GI1 that we measure is way, way, way smaller than this contribution, well, we have an indication, this is just by definition what we call in a natural situation, that we were able to estimate, to guess what one of the contributions to this from UV physics are to this coupling. And then we find that this coupling may or may not satisfy naturally with respect to this contribution, may be of the order, maybe bigger, maybe because there are other contributions, but it could be much, much smaller, in which case it seems that dimensional analysis is not responsible for the size of this object. There is something else going on, and we call this the natural situation. Okay, so let me add a thing. So exactly, so this gives us a way to, given the couplings GI, given GIs, this offers a way a way to decide, to assess the naturalness of any pattern of this set. Namely, if some of these guys is very, very, very small, if some of these couplings is very, very small, you can ask yourself, is this smallness warranted by naturalness? Okay, and that's one particular case. Now, to be warranted by naturalness, it would mean that there exists, that all the other couplings that can contribute via expressions of this type to this given coupling have to be themselves small. And of course, the couplings that contribute here, there will need to be some that transform under the symmetry under which this coupling transforms. In order for this coupling to be naturally small, all the couplings that transform under the symmetry under which it transforms should be small enough, right? Okay. So in that sense, you see that the smallest of a coupling can be understood naturally if there exists an approximate symmetry. Okay. In the limit where the symmetry under which all the couplings that transform under this given symmetry under which our coupling transform are small, then we are guaranteed that all the corrections, all the terms that can appear in the matching can be small. Okay, can be naturally small. And so in other words, these therefore associate the smallness of coupling to the presence of approximate symmetry. And this is the way this was original formulation. Okay. A coupling is naturally small. Coupling G is naturally small if G going to 0 implies the presence of an additional symmetry. In fact, it should be said better if there is an if the smallest of the, yeah, okay, you can say it this way, or if you want, in fact, it should be said more a set of couplings, because if I only send one to 0 and not the others, this is not, oh, well, no, that's correct this way, sorry, it's correct this way. Because if I send this coupling to 0, just the coupling to 0, and not the others that transform, I don't gain any symmetry, and therefore this is not naturally small. So this is most eloquently stated, and this is the way Toft pulled this out of his head, okay, the notion of naturalness. This is 1979. And now, so far, there were just words, and perhaps this is vague, and I think examples can make this hopefully more concrete, okay? And let me just give you an example. And in this example, I will go slightly beyond the very statement here. I will not just say, for instance, with the example, I will show not whether some coupling can be small, but how small can it be, okay? We will be able to estimate that. Now, since I will be using fermions, and the reason I want to use fermions is important, is this. When you consider coupling that involve fermions, there are these famous chiral symmetries that appear with fermions, because fermions are complex fields, and automatically you can endow them with these phase rotations, and the coupling associated with fermions can also be formally may transform under this, and these are the chiral symmetries. So there is the handle of chiral symmetries to enforce naturalness. Okay? But then I will consider real scalars, and there something similar will happen. But the question is, what is the symmetry? Okay, the symmetry that controls the case of real scalars, which actually you can also do in the case of fermions, but in the case of scalars you have just that, was not discussed by Toft. Okay, and this is the slight extension that I am presenting you here. Okay, so let just a little bit of notation, as many of you, okay, normally quantum field theory should be taught starting with the representations of the Lorentz group, and the fermionic representation of the Lorentz group are by spinors. And they come into two types. There is the 1/2, 0, which is the left spinor, and the 0, 1/2, which is the right-handed spinor. Then, as a matter of fact, fermions that have both charge and mass cannot be described by a Weil spinor. They have to be described by a combination of two Weil spinors, and this is what we call a Dirac spinor. So this is why now the fact that the fermions we use on the everyday are like the proton, the electron have charge and mass. This is why the Dirac spinor is so famous. But at the level of fundamental physics of building blocks of quantum field theory, it is the bispinors that we have to consider. In fact, the standard model is built out of bispinors, is a chiral theory. Let me just remind you a little bit of notation, okay? So a Dirac spinor is a combination of two bispinors, the left and the right, the two inequivalent irreducible representations of the Lorentz group. And the Lagrangian of a free Dirac spinor consists of the kinetic term of the right-handed, of the left-handed, of the right-handed, and their mass term. These are all Lorentz. The transformation property of this object ensures Lorentz invariance. Notice that the sigmas here are just these matrices, okay? The sigma bar is the one that controls the kinetic term of the left, and the sigma the one of the right. Then there is the Weil spinor. The Weil spinor is a charge massless spinor, okay? Which is just stands alone. When you turn off interaction, the fermions and standard model are just Weil spinors. Now, a Weil spinor, however, can acquire mass, okay? Thanks to its anti-commutative properties, you can write a mass term, which is Lorentz invariant, and which involves the epsilon matrix, where epsilon here is the antisymmetric 2x2 matrix. Notice that when you do this contraction here, if psi were a boson, this would be 0 by antisymmetry, by Bose symmetry. It's crucial that psi is an anti-commutative variable to make this non-zero. And so this is what you call a Majorana spinor. It has a mass, but it doesn't have charge, because this mass term breaks charge. Okay, there's no phase rotation you can assign to psi, okay, because you have two psis, and if you rotate their phase, this is not. So this is massive, but not charge invariant. And for ease of notation, I will indicate this way. Okay, I will simply write sigma bar the d bar, and the epsilon, I will just forget about it. I will not indicate that. In the standard model, exactly, we have Weil spinors. So for instance, we will see later on that the operator that gives rise to the Majorana mass of neutrinos is something like this. It involves two left-handed leptonic doublets. There's epsilon in the between, and A and B, I don't indicate the Lorentz quantum number, and A and B are just the SU2 quantum number, H is the Higgs field. And this is now the Weil bispinor can also be embedded into a four spinor. That's usually the notation we use. This is the left-handed four spinor, even though the right-handed part is 0. And in this notation, this term here is normally written this way, where C is the charge conjugation matrix. This is just to fix notation. Now, on to something more interesting than notation. Let me consider a first simple example of a quantum field theory, of course, an effective quantum field theory, where I only indicate the leading dimension 4 part, okay? Some of it, not even all of it, because I haven't written the mass of the scalar. I've just a set of the terms in the d less or equal than 4 Lagrangian, the normalizable part of the Lagrangian, the one that survives at low energy, which involves fermions. And this is a theory of one real scalar and two Weil spinors. Okay, and these are the kinetic term, left-handed Weil spinors, and then you can write down Yukav interactions between these fermions and the scalar. Okay, they can be nu1, 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 nu2. I mean, you can mix them, right? There's the 1, 1, 1, 2, and 2, 2, each with their couplings, okay? G11, G12, and G22. Of course, I have to add the Hermitian conjugate to make the Lagrangian real. Now, an example of a structural question of naturalness. Let's say that you have measured G12 and G22. Okay, given this quantity, let's say you know what they are. The question is, how small does naturalness permit G11 to be? Okay, how small allows it to be? Okay, and now to do that, you have to find out, you have to dig out all the possible symmetries you can think of in this system, symmetries under which also the coupling transform. That's exactly the same exercise I did. Well, I presented without doing it in detail for the pendulum. This is just the quantum field theory pendulum, okay? And now, two symmetries I can think of are the independent phase rotation of nu1 and nu2. So it's a U1 cross U1 symmetry. So this U11 is the symmetry under which the first spinor rotates with phase 1, with charge 1, the second doesn't. Okay? This, of course, is not a symmetry because it's broken by the Yukawa interactions. However, if I, should have been a minus here. If I assign the coupling, and this is minus as well. Okay. If I assign G11 coupling charge -2, it will compensate. And similarly for G12, if I assign charge -1, it will compensate that nu1. And G22, of course, there's no nu1, and then it's charge 0. For U12 is the other way around, okay? It's nu1 is charge 0, and so on and so forth. Now, question is, now you see, compatibly with this symmetry, I can write an expression out of G12 and G22 that has precisely the quantum numbers of G11. And it's just this, okay? You can check that this one, okay, is invariant under U12 as G11 and has charge -2, okay? Because it has 2 powers of G12, which has charge -1, okay? So in principle, therefore, according to selection rules, you expect from whatever fundamental theory this theory is coming from, you expect that when you match the fundamental theory to our low energy theory and G12 and G22 are generated, you expect at the same time that a G11 is generated at least proportional to this expression, okay? Now, the question is, what is the coefficient here? And of course, these symmetries cannot tell you what it is, and this is perhaps the more le métier, I don't know how to say it in English. This is the art of doing quantum field theory model building. To figuring out this requires finding, for instance, amplitudes that really give rise to this, okay? So in a sense, this, if you want, it's a little bit dirty thing. Somebody was asking, why isn't this 10 to the -20? Well, in all the cases I can think of, I know how to estimate this by some concrete contribution. And in this case, the concrete contribution is coming from loops, okay? So you can consider, now this is the scalar, this is our scalar. I can consider the coupling, imagine, yeah, I can consider so what is G11 is the coupling that describes the interaction, the trilinear vertex between 1, 1, and 5, okay? And in quantum mechanics, all that is possible happens. So if you have interactions where 1 and 2 and 5 interact this way, and according to this interaction, the selection rule permits at higher order in this interaction to have an object which has exactly the quantum number of G11, then G11 will be generated. And indeed, this loop generates effectively a G11. It generates in the following way. If you compute this loop, okay, well, first of all, you find that this loop is logarithmically divergent, which means that, I mean, of course, we are in effective field theory. We have no right to extend the integration momenta, the virtuality here, at distances shorter or momenta that are bigger than our hypothetical cutoff lambda. Okay, so we will have to cut it off, this loop, at the scale lambda. Okay, we have no right to say that we get anything bigger than that. And the infrared cutoff is just the external momentum. And if you want, is the scale at which we measure the experiment. We do the experiment. And this log represent, if you want, the effect of quantum fluctuations at scales between the cutoff, okay, let's say at scales between this cutoff here and the scale P where we do experiment, okay? But at the high end of this contribution, it is see, the contribution in the high end of the effective theory just merge into the contribution, the virtual contribution of the more fundamental description, right? So they give us an estimate of what quantum fluctuation around the scale will give us. Of course, the presence of quantum fluctuations also at lower scales makes things in a sense bigger because there is this log, but this is a detail, okay? You can say, well, it's a log, okay? And as long as we are not considering orders of magnitude that are like 10 to the 100 scale separation, for all the things that matter, this log can be large, can be 10, can be 20, but it doesn't make a whole world of difference. But of course, it makes things, okay? So if you want to be more careful, you can keep it. So at the end of the day, if you do measurement at a scale that is much below, that is slightly below your cutoff lambda, you expect there are at least two contributions that come on G11 at this scale. One is the one that comes from quantum fluctuations at lambda or above, and you call this G11, okay? And the other is the one that is coming from quantum fluctuation around lambda and below. And so we have been able to identify at least two. And again, naturalness, what is naturalness telling us is that, well, we don't expect, unless there is some deeper relation among parameters, some symmetry we are missing, we don't expect any relation between these two. And the natural situation is when G11 is of the order of the biggest of the two. So in particular, G11, the natural condition, if you want, is that G11, the absolute value is less than, by the way, this C can be computed, or G12 square, G22 over 16 pi square time log of lambda over mu. Okay. So a situation where G11 is 10 to the minus 10 of this, well, is a situation which it just concretely represents the presence of a cancellation between these two contributions, okay, at that order. This can happen, but this is bizarre, and we call this unnatural, okay? And if something like this happens at a very dramatic way, it's part of the curiosity of why we're doing physics, to understand if there is a deeper reason, right? And it's not just an accidental cancellation. So if you want, the naturalness is like a smoke detector, okay? It's just, it detects smoke. Now, whether the fire was caused by some evil guy or just some random fire, doesn't tell you, but at least it's a smoke detector. If the result is perfectly complying with natural, then you say, well, there's no fire going on, okay? And let's move to some other question. I mean, not saying that, okay, let's do physics, but there is, let's put our attention somewhere else, okay? Here is another example. Here it's an example of a theory with only scalars. Here, let's say that instead of fermions, you have just two scalars, phi1 and phi2. And the leading order in the renormalizable part of the Lagrangian, let's forget the mass for a moment. Let's just consider the dimension 4 couplings that are those that matter mostly at higher scales. As you have seen in the bit, in order to have a scale separation, to be able to describe a theory in terms of a few parameters, I have to have a separation of scales, right? Otherwise, it's like when we were doing this charge distribution. If you don't go far away, you cannot describe it in terms of a few parameters. You really need to know what it is, okay? Here, if you want to do quantum field theory with a few parameters, it's clear that there must be a scale separation. And then let's say we're in the intermediate range where we can neglect the mass, and let's just focus on the potential, on the quartic part. In a theory where we have a symmetry, phi1 goes to minus phi1, phi 2 goes to minus phi 2. Now the question is, given, like before, G12 and G22, what about G11? What value of G11 can we think of compatibly with naturalness? Okay. Now, you may say, oh, let's do like the other time. We just think of some symmetry, U1, but these phi's are real. So there's no such symmetry you can use. What can we do? Okay, what can we do? Well, let's start using, let's do the following, okay? Before looking for the symmetry, let's play the game we played before. Before we, play the other way around. Before we found the symmetry, and then we found some diagram that gives a contribution, an effect that is compatible with the symmetry and confirms our expectation. Let's do the opposite here. Let's now use what we learned earlier. The diagrams give contributions that comply with whatever symmetry we may not have yet found, okay? We will think later about what is the symmetry behind this result, but let's first look for the diagram, okay? So let's do as before, and well, that's easy, right? We want to find the contribution to G11, okay? So we want to look for a contribution to the amplitude with 1, 1, 1, 1, and this is easily found at one loop, okay? Let me draw well. I'm drawing like shit, okay? Let's do like this. At one loop, this is pretty easy. Okay, here is 1, 1, 1, 1. Here you have 2, 2, and this is G12. Okay, do you see me? Let me write it better. G12. So, and now you estimate it precisely as before, and this is going to be some coefficient that you can compute, okay? It's order 1, okay? And then it's G12 square, 16 pi square, log, again, let's assume there is a cutoff, the scale at which we are doing the experiment. Let's say the P is the momentum flowing in here, okay? So this is what, and therefore let's say, and therefore our estimate is that G1, our naive estimate based on this, we don't talk yet about naturalness because we don't know what symmetry is going there. But if there is a contribution to G11 of this order, it means they will be allowed by some symmetry. Okay, there's a contribution like this of this order. Therefore, we expect the expectation is G11 at some scale P mu to be less than order. It cannot be bigger than order. It cannot be smaller, sorry. Oh, damn it. Here's the other way around. It should be bigger. What am I doing? Okay, it should be bigger. Okay, to be smaller, you will need a cancellation. Then G12 square, 16 pi square, log of lambda over mu. Now, the same as before. Now, the question is, what is the symmetry behind this result? Is there any guess? Let's take a little 30 seconds break and also ask questions, because you see, I'm saying things the other way around. If I say wrong things, even on the things I understand well, then you would be confused. So this is a good moment to stop and perhaps to collect the pieces to see whether things are flowing. Any questions? Internet issue, sorry. Niklas, are you saying that you cannot hear me? Oh, you should unmute. No.
Yeah.
Hello,
just
no.
wondering, in the last example, there was no enhanced symmetry when you take G11 to 0, right? Or am I missing something?
There is.
There is. Okay, so what is
Well,
it?
there is when you send G11 and G12 to 0. As you see.
Yeah, right.
As
But
you
not
see,
when, but not yeah, exactly. But not just not this example. I'm talking about
oh, yes. Bravo. Yeah. You're right. You're right.
which is why I was wondering. This is an
you're right.
example
Toph was
of
right. If I only send G11 to 0,
there is no enhanced symmetry.
there's no enhanced symmetry because
So-
the symmetry is broken by this.
Exactly. So that's why I was trying to see if I understood at least the point that.
But also it's also broken. See, if you send G11 and G22 to 0 together, then there is a symmetry.
Sure, but okay. So I was because I'm used to thinking about naturalness as okay. You take whatever parameter you want to
in
0,
order
and you
to make
see
this
the
natural, you have to set to 0 either this or this, and there are two
Yes.
different subgroups of this that control that. Is this clear?
So this is how you sort of this is how you can see it. Yes, I see.
Yes.
Thank you.
But you're right, I should have said it. So what about here? Is anyone with a guess? Let me ask you, one thing that you see is that if you have a theory and the theory is free, okay, is this property robust? Do quantum correction undo this property? Of course, it's intuitively obvious that the answer is yes, it's robust, right? Oh, there are chats. Maybe rotating in phi1, phi2 space. That's also a possibility. That's also a possibility. That's also a possibility. Okay, right. In this case, you can also use that. Definitely, you're right. Mehmet is right. Okay, Mehmet is saying rotating in phi1, phi2 space, and then the G11, G12, G22 will be a two-index tensor in this space. Okay, and you're right, and you can play also along these lines. Very good, Mehmet. Or somebody else is saying that there is a shift symmetry as well. There's also shift symmetry, but the selection rules of shift symmetry are not good because it's not linearly realized. Okay, so they're not symmetry under which these couplings transform linearly. There's actually a symmetry which is quite ubiquitous and very useful, and it can apply also in other cases where there is no alternative. Okay, and this is the symmetries of free field theory. And this is what I want to spend 10 minutes on it. So consider free field theory, because this is also what will be important for, say, the Higgs. All the stuff you said, the shift symmetry, the rotation are very good, but I think this is more ubiquitous and more robust in general. Okay, so let me show you this. Okay, so consider free field theory. Okay, so free field theory, we can solve it exactly, and the Hamiltonian is just a direct sum of harmonic oscillators, where omega k is just okay, the energy. Now, the property of this Hamiltonian is that it commutes with the number of quanta in each momentum cell. In other words, the number of quanta at each given momentum is conserved. Particles are not created and not destroyed. You start with n particles at a given momentum, and you end up with n particles there. And this is true for all momenta. Okay, and the question is, what symmetry is this, and how we view it in the if you want in the neutral procedure? What transformation do we associate to this symmetry? And the quickest way to see what's going on with what is behind the symmetry is to write the action in momentum space. rather than in position space. Just do the Fourier transform over all space-time, and then your action will be 1/2. Let me write it properly. Phi hat of minus p square minus m square, phi hat of p, where phi of minus p is phi of p star, the Fourier transform. Now, so the fact that the field phi is a real space-time field implies that this Fourier transform satisfies this reality condition. When you take the star, you get the Fourier transform at opposite for momentum. Now, the fact that phi is complex, the fact that in momentum space you have a complex variable, allows you to think of phase rotations. In particular, you can think of the following transformation. You can rotate every component at any given momentum by a phase, okay, which depends on the momentum. The only thing you need to ask to protect this reality condition is that this phase is an anti-symmetric function of the momentum. Okay, if it satisfies this, then the transform field satisfies this property. Okay, and now, in fact, now precisely this property here, the fact that theta of minus p is minus theta of p is what guarantees that the quadratic action is invariant. Okay. So this is a huge symmetry of free field theory. So free field theory is the system characterized by this huge symmetry. Okay. What does this symmetry imply on fields? Okay, on the space-time fields. Well, to do that, let's write this function theta, okay, as a series. We said that theta should be an odd function of p. So there will be a linear term, a cubic term, a quintic term, and so on and so forth. Okay, and now let's work at infinitesimal level in these parameters. Okay, when we expand this phase, okay, at first order in these parameters, multiplying by p mu is like taking the derivative with respect to x along mu, and multiplying by 3p's is like taking 3 derivatives. So the transformation of phi under the symmetry infinitesimally is given by this. Okay, and the first term, you already know it, is just translations. Okay, but this is a new thing. Okay, and this is, it looks like translation, but you're translating with 3 derivatives and then 5 and so on and so forth. The corresponding method currents, they will have correspondingly more indices. Okay, there will be higher spin currents. Okay, and very much like the translation symmetry implies the presence of a conserved energy momentum tensor satisfying d lambda mu equals 0. Okay, and very much the same way, these other things you will have conserved currents that involve 5, 6, and more indices. Okay, and the conservation. Okay, well, the conservation in the case of the energy momentum tensor, when you consider particles, we know what implies conservation of energy, right? For momentum, is the conservation of the sum of all the energies of the incoming part, of incoming, the conservation of the total energy of the incoming, that is equal to that of the outgoing, and similar for the free momentum. Now, if you have, in addition this, you have that also these nonlinear polynomials, monomial, the sum over all particles of not p, but p cubed and p to the 5th and all that will have to be conserved. And this, of course, you can easily be convinced this implies that no interaction is possible. It's the usual, this is one of the essence of the Coleman-Mandulan theorem that states that in order to have an interesting S matrix, the most general symmetry you can tolerate is Poincaré with a Lie group. Otherwise, you need a symmetry which is a graded algebra, that is to say, supersymmetry. And this you already see it, right? This symmetry, these are conserved quantities that carry Lorentz quantum numbers, so they transform under Minkowski, so they do not commute with the Lorentz algebra. So this is an extension of the Lorentz algebra. It implies these weird additional conservations which lead the theory to being free. And in fact, we know this is precisely what characterizes free field theory, but we see it there, right? This, you see it already in mechanics, right? Well, okay, we can get back to that later. But so this is forbidding interaction. Okay, so oops. And well, this can also be seen more directly, okay? Let me just say it very quickly. When you compute the quantum effective action, the 1pi effective action in this theory, as you are familiar, it will be written as a sum over vertices, okay? There's going to be the 1-point function, 2-point function, 3-point function, and so on and so forth, okay? And in this theory, you only have even point function, okay, let's say, because, well, it's free field theory, we know what it is, but let me at least formally tell you, okay, we know it's free field theory, okay, so there's little to say, we know that this is trivial, but it's interesting, it's still interesting to see how the symmetry tells us that this is free field theory, okay, even though we already know it. So you look at the effective action, which is the 1pi effective action, and this will have to respect all the symmetries, okay? And so it consists, of course, translations is a symmetry, so there's going to be this delta function. We write it in momentum space, and then you have the vertex, the endpoint vertex, okay? Of course, these P1 and Pn satisfy this condition that this will be zero momentum conservation. Now, you're easily convinced, it's very quick to see that invariance of this action under the symmetry we are discussing, the symmetry under which phi in momentum space transforms by an arbitrary phase, okay, so a phase that satisfies this reality condition. If this is a symmetry, then it's just easy to check that the only gamma that can be non-zero is the 2-point function, because all the others, okay, they cannot compensate. If you have 3 momenta that are at different points, you cannot compensate. It's only because this symmetry here allows to cancel the phase only 2 by 2, one and the opposite. And this is realized only for the 2-point function, where the 2 momenta are forced to be back to back, and therefore the phase cancels. Okay, so this is the symmetry that characterizes free field theory. Is this infinite set of higher spin charges associated to higher spin currents. Now, this is the symmetry that characterizes freedom, free field theory, and therefore interactions all break this symmetry. And therefore, all the couplings can be viewed as spurions transforming under this symmetry. Okay? If you want, in a sense, the presence of this symmetry is what is telling you formally that free field theory is a natural theory. In other words, that if you take a theory and you take its coupling and you make it smaller and smaller and smaller, that's a natural procedure in the sense that if you make them all smaller, small, because in the limit where all the couplings go to 0, there is an enhanced symmetry, and this is this higher spin symmetry. This is what characterizes free field theory as a natural limit. Even though it's obvious because you can solve it, but this is the stability of free field theory from the point of view of the 12th principle. Of course, it's using a canon to kill a fly, but that's okay. Now couplings now can be used as spurions, okay? And now you can use this symmetry to see how couplings can fit into one another. In the end, the information that you derive by this is precisely the one that you get by computing loops. But you associate it to a symmetry. So you can say, this is very much like the pendulum, okay? And let me show you this, okay? So take, for instance, phi to the fourth, okay? Add the quartic interaction, okay? And now you can view this in momentum space as you can extend lambda formally to a vertex that depends on P1 and P4. It's like a field that depends on 4 coordinates, x1, x2, x3. And then when you go to momentum space, P1, P2, P4, you just extend it, okay? You just formally treat it as this quadrilinear field, a certain field that depends on 4 coordinates, okay? Rather than being, is a non-local field. It's a field that depends on 4 coordinates, okay? And now this interaction can be formally written this way. Of course, the real value is just this is equal to just a delta function, okay? It's just equal to this delta function. That's it. This is the physical value, but we can treat it as a formal general thing, okay? And this is the expectation value if we want. Now, formally, we can regain our symmetry, the symmetry we had beginning, if lambda transforms in a way as to compensate the phase rotation of the fields, okay? So this, together with this, is a symmetry. And this tells us how lambda can enter in relation with couplings, okay, when we do the matching or when we compute loop. In our case, in the case we had before, okay, we can consider a phase rotation of free field theory independently for phi 1 and phi 2. Okay, so phi 1 will rotate by theta 1 p1. So in particular, that means that g12 and phi 2 by theta 2. So let's say if you take g12, it's a vertex, g12, there's no g12 squared, g12 here, okay, it's a vertex which involves 2 phi 1s and 2 phi 2s. So the first p1, p2 are those associated to phi 1, and the second ones are 2 phi 2. So now when I rotate phi 1 and phi 2 by their respective phases, I can compensate their rotation if g12 transforms in the following way. Okay, it's from p1, p2, p3, p4. The first ones rotate by the phase of phi 1, theta 1, and the other one by the phase of theta 2. G11, it's purely phi 1 interaction, so it all rotates by the phases of phi 1. And now it's clear that G11, which is the coupling we cared about, we wanted to assess its naturalness, has exactly the same quantum numbers under these higher spin symmetries as this combination. Okay, this is a combination of G12, P1, P2, P3, P4. Okay, right. And where if I take the momentum here opposite, I compensate with their phases, okay? Because G12, the theta associated with opposite momentum is the opposite phase, and so they compensate. And this is precisely and then on this pi 5 and p5 and pi 6, you can even sum over all of them. And that's precisely this loop here. This is precisely the statement, perhaps in a complicated way, but that this is precisely, this is the same as saying that this loop is possible. This is what describes that. But this is just to tell you that even this computation done this way, even this relation, beside all other possible symmetry we would have thought of, can be understood by a very simple phase rotation, very much like in the case of the, and these are and this symmetry is ubiquitous. You see that this is very flexible. It exists all the time. Okay. So again, we expect this relation here. So the simplest example where just to see the power of this symmetry is to consider the mass in phi to the fourth theory. So let me consider a phi to the fourth theory, very much like the one of the Higgs. I will get back to you in a moment. And then you have higher order interactions. And now the question is, assuming this theory as a cutoff at scale lambda, okay, and assuming this is the coupling, what do selection rules tell us on this mass? What should we expect based on naturalness? Well, okay, the mass under our phase rotation symmetry transforms precisely like an object like this, like it transforms with the two phases associated to phi in pi 1 and pi 2. They can be extended, both the mass and the g, they can be extended to object carrying as many momenta as there are legs in their vertex. Here there are 2, here there are 4. So this is the transformation of the symmetry. Then there is, of course, the notation, which is just dimensional analysis. And then it's a piece of cake to check that m squared, the mass, has the same quantum number as lambda, where you take 2 of its 4 momenta to be equal and opposite. Okay, the little g. Damn it. And times the scale, which fixes the just dimensional analysis. This is dilatation. If you want, this is the dilatation charge. This transforms as an object of charge 2 under dilatations. There should be lambda squared. And this transforms in a certain way under the higher spin symmetry. And you can match that with this particular G, okay, where you choose K minus K, so that you expect that the mass will scale like this. And indeed, this is what you get when you compute, when you try to estimate by using this loop. Okay, that's precise. Okay, let me just put G here. Okay, so that's an example where this applies to something that starts being interesting, like a mass term. And the reason why this is interesting is because masses are precisely the things that control mass hierarchies. And mass hierarchies, the separation of scales, is the essence of all our construction. Without the separation of scales, we cannot say that things get simple, okay, at low enough energy. If we cannot go far away in this electrostatic potential, we don't see the simplicity, we just see complicated situation. And again, this we can also see the same, let me just go very quickly, the same reasoning can be applied to the pi plus mass as we did last time, okay, the mass. Now we extend the electromagnetic coupling to a spurion that depends on 3 momenta, the 3 momenta that enter the vertex. And again, you match the higher spin quantum numbers this way. So again, the result we found yesterday could also be motivated using this symmetry, okay? And this is as good an estimate as the one that Galilei did as one of the first steps into modern science. Maybe it's interesting to see where this will not work at a certain point. This will go beyond, to go beyond Galilei. We're still at the GGI, but let's hope we'll go beyond. So let's hope in a sense that we will discover unnaturalness. But just continuing on that line, this will be the expectation. Now, let me take a little break. Let me try to address one of the questions, and then we will move on to the next thing. Who is that wants to talk?
Hi, Riccardo.
Hello?
Hi.
Hey.
How do I interpret this phase rotation in real space? That's that one question I have. And can you please elaborate the dilatations that you
this
showed?
Phase
like
rotation, as I said, this phase rotation, as you see, you mean a finite phase rotation?
Yes,
well, that's complicated. Yes. If you have only a linear term, this is just a translation. You're asking me a finite transformation.
Right.
Yeah. Well, it's a complicated change of coordinates. Figure it out. I've never done it.
Okay.
I've never done it. I've only done it at infinitesimal level. But yeah, you can iterate it using yeah, it's a complicated change of coordinates, right? I wouldn't be able to write it down. I've never done it. Right, it's a good question.
And the next question will, and the next question is like related to the other slides that you showed, like the next slide maybe. Yeah, if I can you scroll down maybe? No, the next one. So here you are saying about the dilatations, right? Like that you change mass, you change your...
Here the dilatation. Here the dilatation.
Right. So like my question is like, here we are trying to argue why m squared should be proportional to the quartic coupling. That's the argument that you are trying to...
it's proportional to the quartic coupling and to whatever mass scale you have in the problem.
Right, but then I don't understand, like, why do you like even consider dilatations here? Because until, like, so the whole starting point would be that, okay, if I know that there is a cutoff scale, then it's just where the loop cuts off. Like, you don't.
Well,
you
it's
don't
the
get
same thing. I'm just telling you that this argument that you call the loop cutoff is just, I'm just saying things that are obvious in a different way, just to connect them to, I just want to insist. See, my goal is to run the risk of looking ridiculous. My goal is to show you that all these estimates are nothing but selection rules. There's nothing else.
Okay.
This is all I want to tell you. And that
Okay.
if somebody comes and tells you, oh, quantum gravity, this is zero in quantum gravity, then you say, well, you sure. Then you go and teach introductory physics and you show dimensional analysis, you say, well, you say this doesn't always work.
Mm-hmm.
You see what I'm saying?
Okay.
I've seen colleagues who thought that there was something deeper here than just selection rules.
Mm-hmm.
I'm insisting there's nothing else than selection rules. Now, it doesn't mean that that this estimate is correct. It just tells you that according to selection rules, this estimate, this is what you get, okay, in any, when you do any matching. The fact that then in the fundamental theory, there may be contribution that cancels, that's always possible. But that's, in a sense, a more rare occurrence. The typical occurrence is that selection rules work well.
Okay. So if I can, sorry if it's taking long, but I just want to make it clear. If I take you back to the first lecture that you started, that if we go back to the charge distribution problem. So
yes.
In this case, you are saying that we are very far. In that case,
in that case, we have the freedom to go very far, right?
Yes. So in that case, I have this SO3 symmetry, and then because of that, there are certain coefficients of zero. Is this what you would be saying in the?
No, there I was not discussing any naturalness, right? There I don't think I discussed naturalness there.
No, you did not. But I was just interpreting this lambda as 1 over r, and large distance means I'm taking r to infinity. So I'm just trying to connect those two pictures, nothing else. Maybe
no, this lambda here, this capital lambda here is a, is 1 over a, the size of the object.
Yeah. Oh, okay.
It's not the distance. The distance where I am is the energy of my experiment. Of course, if little m is large, that I cannot take the energy smaller than m, right? So then I cannot even go to small energy.
Okay. Thanks. I understand. Okay. Thank you.
Francesca.
Thank you. I was wondering, are we allowed to keep proceeding in this way if the couplings are big and non-perturbative? Because if couplings are perturbative, we can somehow say, okay, let's pretend they are zero. But if they are very big, maybe the physics completely changes.
Yeah, if they are big, you cannot even, you don't even call them coupling, okay? So if the coupling is big, what does it mean that it's big? How you define a big coupling? So these couplings are all defined as perturbations of something, in a sense that if you have something big, then you put it in the, say, let's say the following. Imagine you have a coupling that becomes big, and like in the CFT example I was showing before, then this will be part of the, let's say you have a theory that flows to a fixed point, the coupling becomes large, and then it's part of the leading Lagrangian. And then you study all the perturbations around it. Okay. Now, a coupling that becomes big, like in QCD, it gets. You could use either that coupling or the scale where it becomes big as inputs in your selection rules. So as you see, when I did the pion mass, I did not use alpha strong. I used just lambda QCD. But the fact that I was using lambda QCD is just a signal of the fact that the coupling was so big that it didn't make sense to use it, and I used some other manifestation of that coupling. As long as you use a manifestation of a coupling, that's enough. That's taken into account. I don't know whether.
So let me rephrase my question. At which point do selection rules break? Can we always use
I mean, show me an example of a strong coupling.
I actually do not have it because I was thinking
Exactly. That's the problem.
See,
in practice, it's a good question. Okay, but yeah, I mean, all we understand in quantum field theory is this: we have a fixed point, which is a conformal field theory. We perturb it, and then in the IR it will flow to some other theory, which either has a gap at the scale lambda, or it goes to a new fixed point. And then if at this scale lambda means that the coupling that became strong, we convert it into this scale. Okay, and then from that point on, you describe physics in terms of the perturbation of another fixed point, of yet another fixed point.
So it is a way of avoiding non-perturbative theory.
No, it's not that to avoid. It's the way of no, we don't avoid it. We no, you say, because we take them into account, right?
Also in Italian, I don't know.
In other words, the fact that I use lambda QCD instead of the coupling means that I'm using arbitrary powers of this coupling already, if you want, in a sense.
Okay.
See, using lambda QCD and using G strong is the same as the same content. Okay. Now, at the scale of 1 GeV, at very high energy, let me put it this way, Francesca, at very high energy, G strong is small, and it's convenient to use the symmetry I'm describing here of free field theory under which this coupling transforms.
Yeah.
By the time you get at 1 GeV, this coupling is so strong that there's no point of using that symmetry. It doesn't give you any constraining power.
Yeah.
The only thing you can use about this coupling is the information that this coupling became strong at 1 GeV, and that's lambda QCD.
Okay.
That's what I'm using.
Okay, thank you.
I believe this is a fair illustration of what I'm doing.
Okay, fine.
But it's not clear, I'm afraid.
No. I don't know if you can still hear me.
Yeah.
I'm satisfied, thank you.
Mm-hmm. Okay.
Riccardo, there is a last question in the chat.
No, I don't see any.
Chat.
No, this is not the same. He's asking whether this includes conformal symmetry, and the answer is no. The answer is no. If we can discuss that later on, okay? Good. Now, as usual, I am far behind. So what I wanted to start now is the discussion of the standard model. I would now like to apply the perhaps still a bit fuzzy in your mind ideology that I've been giving you. I hope, things may get clearer in the future. If you think more, if you ask me more, perhaps I can explain better. And I also learn to explain better and think of all ifs and then that I haven't perhaps thought about. But now I'd like to apply this to the standard model, to really now apply the ideology I've been developing, starting with the ideology of effective field theory, simplicity, accidental symmetries, to the standard model. And then naturalness. Now, it looks like we've been talking about naturalness all the time, but remember at the beginning we were talking about simplicity, the emergence of renormalizable theories, and all that. Okay? So, how do I define the standard model? The modern way to define the standard model is to define it by its field content and its gauge symmetry. That's it. So the standard model is defined by the multiplets it has and the gauge symmetry. With this, according to the modern perspective, given these fields and this gauge and their gauge transformation properties, you should be expecting a Lagrangian that involves arbitrary high dimension terms. All the terms you can think of should expectedly be there. Okay. Now this is distinguished from the naive and now obsolete and very, okay, I don't want to find the word. I'm not getting the word. Obsolete. It's okay. Okay, obsolete version where the standard model is this Lagrangian with only normalizable operators, and whatever operator is not in this Lagrangian, you say, oh, this is beyond the standard model. I'm fed up of this definition. I think it's time to grow up. Okay, so the standard model is defined this way, and then we write the most general effective Lagrangian. Okay, we write the most general Lagrangian, and we interpret it as an effective Lagrangian. Okay. That is to say, as an expansion in inverse power of some yet unknown microphysics cutoff lambda UV, which is 1 over A, which is the length scale, below which we see some real dramatically new physics. Okay. So let's therefore analyze what we know experimentally and what we know structurally about the standard model and assess it. Okay. So let's look at look at all the terms we can write down and let's analyze them. Okay, and let's organize the discussion in terms of dimensions. Okay, so let me start with the part of the Lagrangian which involves only operators of dimension 4. Okay, this is the this is just the kinetic terms, the gauge interaction, okay? But there are also the gauge interaction among gluons, among Ws. There's the gauge interaction with fermions, the Yukawas, and the Higgs quartic. Now, what is really interesting about this renormalizable part is that all the things, all the couplings we have here, we have seen. These are the couplings that make particle physics. In fact, this is the last coupling we have seen, the Higgs quartic, which is the one that determines the Higgs mass in terms of the Fermi constant. Or if you want, without talking about the Fermi constant, this is the coupling that determines the values of the Higgs mass in units of the Z mass. Okay, the ratio is simply lambda over G squared. Okay, of gauge coupling square. Okay, so beautiful. All we have, we see. And then we go to the next layer, okay? And amazingly, as soon as we go to the next layer, we encounter all things that we have not seen. Not only we have not seen, but we have strong bounds on these coefficients, okay? We start seeing dimension 5 operators, which, like this one, okay, involving 2 fermions, not fermions and antifermion. Remember, here we have fermion, antifermion, fermion, antifermion. When we go to the next order, we see objects that violate fermion number because we have 2 fermions together. We have interactions involving 4 fermions or with arbitrary orientations in flavor space. We have interaction, and in particular, we have interaction like this that even allow, well, okay, all amazing phenomena like proton decay, other things. We have interaction like this that allow not seen phenomena and quantities like electric dipole moments, things that are not seen. Okay. So how to explain? I mean, this is just a fact, right? The renormalizable part we have seen. The non-renormalizable part we either haven't seen, or let's say in this case, this is what would contribute to neutrino masses. We know it's very, very, very tiny. Okay. So what would you conclude based on what we have been saying so far? Well, this is precisely, we're looking at the cow from very far away, okay? We just see the leading long distance phenomenon, and we don't see the short distance physics because, well, because the scale lambda is pretty large. It's very, very, very large, okay? So this sharp separation between what we see and what we don't see, the fact that the dimension 4 operator or dimension 0 coupling, those that are important at all scales, we see, and those that are becoming unimportant when you go below the cutoff quickly, we don't see, or they're very, very, very tiny, it's truly indicative that the next layer of physics is high, okay? In other words, assuming a lambda that the next layer is much above the scale where we do measurements, that is to say the point-like limit of the standard model nicely accounts for what we see. However, the story is not just this. Partly I've cheated and partly I've forgotten things, and I have so far only talked about operator of dimension 4 and higher. There are also a few operators of lower dimensions. Well, actually, there is one operator of dimension 4 that for which I cheated, okay? And this is the famous GG dual. I didn't write it well here. Here there should be no this, okay? It's GG dual, not G dual, G dual, okay? And this is part of this Lagrange. It's the only exception which we haven't seen. We haven't seen, and in fact, we know that its coefficient has to be tiny. Tiny in a way that demands an explanation. In the sense, it doesn't seem natural, okay? But here we have some nice explanation. I will comment on that later.
Riccardo, sorry, a reminder, could you wrap up in a few minutes? That's then there is the lecture.
Right, yes, you're right. So next we have a dimension 2 operator, okay, which is the Higgs mass, okay? And there we already have indications that the mass of, we've seen in the example of the last example I did when I discussed naturalness, then these masses tend to come out controlled by the cutoff times some combination of couplings, okay? And couplings in the standard model are not that small. So in other words, we expect this thing to be going like this fundamental scale times some coefficient, which we will have to determine, try to estimate, try to guess what its natural range is, but according to naturalness, we don't expect it to be much less than 1. We will see that better later. But in other words, if this scale is whatever it is, say much bigger than TV, then you can, the coefficient, in order to explain the mass of the Higgs, which we know it's about 100 GeV, this coefficient would have to be small. In particular, the rule would be this, okay? If lambda is 10 to the 10 TeV, well, then this coefficient is 10 to the minus 20, okay? And things are not over, because the lower you go in dimensionality, things get worse. And then there is what is sometimes called the elephant in the room, okay? And this is the vacuum energy. And here we are really in trouble, okay, it seems, because here, what is this? This is a vacuum energy. According to selection rules, this is controlled by the whatever scale we can think of in our system. So for instance, if we put here the electroweak scale, we get a contribution that is 60 orders of magnitude bigger than the one we observe, okay? So this, here, there is a stark violation of naturalness. There's no doubt here. And the if you want, astonishing thing is that we have really no explanations other to go away from naturalness here. And of course, one could have a whole discussion about this. I won't, okay? One very naive and I don't think acceptable, but this the question is mostly perspective. You first have to give a story and then go back. Is that, well, this involves gravity, it's a different story. We know there's been inflation. So that this is clearly to do with the history of your universe. maybe quantum gravity. I don't think this is, I think this is just an excuse, okay? I think I would just leave it out. The reason why I would leave it out is because we don't have a mechanism, a convincing mechanism, okay? And let's see whether we can find convincing mechanisms for whatever other problem we can have. If we don't, then we may go back to this and see that whether there is a relation, okay? So in what follows, I will focus on this issue. But before going to that, I really want to analyze this in more detail, this success of the standard model. In other words, how clever the standard model is when you focus just on the part that is the equal for, the part that, if you want, we have observed, okay? And this is what I want to say here is what I would call is the magic of the standard model, of the d equal 4, the one that is normally called the standard model, okay? And there are a few things I will explain.
Riccardo.
Yes, I'll stop here.
Yeah, it's better if you...
I'll just stop here and I'm just saying that the next lecture will be all about this, okay? I am way behind in the schedule. Well, that's it. That's the way it is. Sorry. Thank you for being patient. I'm done.
Thanks, Riccardo. And yeah, there will be another lecture tomorrow, and then Francesco put the link to the GGIT seminar for the students who want to join.